Alright, in this video we're going to talk about section 11.5, which is lines in space. So first, before we talk about lines, I'm going to reiterate a topic about vectors that I discussed a little bit earlier. So I didn't use this term, but we're going to define what's called a position vector. So a position vector is a vector with its tail, or initial point, whichever one you want to call it, at the origin. Oops, sorry. Since vectors can move, since vectors can quote unquote move anywhere as long as their magnitude and direction remain unchanged, every vector has a corresponding position vector. So I've discussed this before, that we can take a vector and move it so that its tail is at the origin. When we do that, that vector is now called, we call that a position vector. So for instance, if we're in the XY plane, and I want to define a vector based upon, say, the point, let's say -1, -2. So we'll put a point right there and we'll call that P. And it has coordinates -1, -2. And another point Q we'll put, let's say is 3, -1. And I want to talk about the vector. So we could talk about the vector PQ, which would be that vector right there. So that's the vector PQ. But if I actually wanted to write out the components of this vector, then we would do that the usual way. So PQ, down here, PQ, we'll do 3 minus the -1. So 3 minus -1, and then -1 minus -2. -1 minus the -2. So now, simplifying this, so we get 4, and then the -1 plus the 2 gives us 1. So now, if I look at 4, 1, and I go over 4 units, well, my x-axis is a little short, but if I go over 4 units to the right and 1 unit up, and I plot a point right there, say right here, that's the point 4, 1. Now if I draw a vector from the origin to that point, then that's the exact same as this vector PQ that we have right here. All we've done is we took this vector and we slid it so that its tail is at the origin, and that vector is given by 4, 1. So instead of explicitly defining it based upon these points, what we do is we actually define it based upon it starts at the origin, and all we need is its endpoint. So a position vector always is going to start at the origin, and what you see when you see the vector written out will be the point where its tip lies. All right, so we're going to oftentimes use position vectors. So I just want to introduce that terminology, even though we already discussed the concept itself. All right, so now that we have position vector, we can talk about the vector equation of a line, or an equation of a line. All right. The vector equation of a line, and we're going to use a script L to represent our line, is, or just to name our line, is, and leave some space between this line and the next line, because I'm going to have you write something right above this equation. I'm going to write is the vector R equals the vector R naught plus T times the vector capital L. So please make sure you use a script L there and a capital L here, because these are two different L's, and we don't want to confuse the different L's that we're using. So now I'm going to talk about what each thing is here, where R naught equals the vector x naught, y naught, z naught, is any position vector with tip or terminal point P naught with coordinates x naught, y naught, z naught on the line L. So underneath this, put a little squiggly line underneath that P naught on the line L, because in finding a vector equation of a line, this is going to be one key component that you need. So I'll repeat it over and over again. So what do we need to find the equation of the vector equation of a line? One, we need a point on the line, which we call P naught. And also in our equation, we have our capital L. So the vector capital L equals the vector with components A, B, C, is any vector parallel to script L, and T is any real number. All right, so we need a point on the line, and that's script L. Put a squiggly line underneath that part. Script L is any vector parallel. Sorry, capital L is any vector parallel to script L. So those are the two key components that we need to find a vector equation of a line. So I liken this to, so remember I said leave some space right above that. I liken this to what you all have known in the past for finding an equation of a line in 2 dimensions. So remember that this that we're talking about here, this will work in both 2 dimensions and 3 dimensions, because we're working mainly in 3 dimensions because this section is called lines in space. But from what you all have known in the past for a line in 2 dimensions, oftentimes we think of the formula y equals mx plus b. So this r, this vector r, would be like our y. So in parentheses up here, this is like y equals the mx. This L, the capital L, would be like our slope. So that would be like our m. And then the x would be, this t would be like our x. So this would be x. That would be like m. And then our y-intercept would be like this r naught. So you can kind of think of this in that similar form, y equals mx plus b, where these are the corresponding aspects of the vector equation of a line. Key thing that you all need to take from this is if you need to find a vector equation of a line, script L, you need a point on the line and you need a vector that is parallel to the line. Those are the key aspects that you need. So I will kind of sketch what is going on here in talking about a vector equation of a line, just so we have a clear understanding of that. So we have our coordinate axes. And I could have sketched this in 3 dimensions, but this is for understanding purposes, so it's a lot easier for us to understand it if I sketch it in 2 dimensions versus sketching a line in 3 dimensions. You get the concept the same with the line in 2 dimensions as you will with 3 dimensions. So here's our line. And remember, lines go on forever in both directions, so we put our arrows on there. And we call our line script L. So where does that equation r equals r naught plus TL come into this? So we can take some vector, we can sketch some vector L if we want this parallel to that. Well, that's not really what I'm trying to get at. What I want to get at is that the r itself is not the actual line. It's some vector. So, and it's a position vector in particular. So if I say, what we'll do is we'll draw these position vectors. So you plug in a particular time t, say whatever, t equals -3. You plug in t equals -3 to that equation r, then it gives us this vector. And this vector, what it does is the tip of that vector is what's on the line. So whatever, say now you plug in r equals 0. And you might get that. You plug in r equals 1, and you get that. You plug in r equals 3, and you get that. And you plug r equals 7 in, and you may get that. So what is actually happening with that equation, r equals r naught plus TL? So all of these will be different r's. They will not be r naught, they will be r. So what we have is, as t varies, script L is traced out by the tip of R. All right, so R is going to trace the entire line for us. And where is capital L? Capital L is any vector that is parallel to this line, whether, let's say, we make this your capital L. That's just some vector that's parallel to a line. And your R naught will be any point that's on the line. So R naught could be the tip of, could be any one of these particular vectors, because the tip of that R naught is going to be on the line. So any one of these or any vector that has tip on the line. But really, you can just think of it as a point on the line. You don't have to think about R naught in particular. You want to think about P naught. So as long as you have any point on this line and some vector parallel to the line, you can find the equation of a line. All right, so that was the vector equation of a line. There are two other forms that we'll consider. We'll consider the parametric equations as well as symmetric equations. So I'm going to introduce those two, and then we'll look at some examples. So now, note that, let's do this, R, and leave a good amount of space, equals, and leave some more space, the vector R naught, and then another gap, and TL. So this, the R, this, what it's going to give us, according to this, it's just going to give us the x, y, z coordinate on the line, or in this case, x, y, but I'm going to use x, y, and z. So our output is going to be wherever we are on the line. So it's going to give us a point x, y, z on our line, equals R naught is always x naught, y naught, z naught, plus t times our L, we said was A, B, C. So all I did is plug in the different things into this formula the way that they were defined. All right, so this, now we just use our knowledge of vector operations, and this is the same as x naught, y naught, z naught, plus, remember, t is any number, so it's just a scalar. So we multiply this scalar times that vector, then we end up with AT, comma BT, comma CT. All right, now we can add these two vectors that are on the right hand side, and we get the left hand side XYZ is equal to x naught plus AT, comma y naught plus BT, comma z naught plus CT. So now that gives us our next way that we can write the equations of a line. So we have the parametric equations of a line script L through any point P naught with coordinates x naught, y naught, and z naught, and parallel to any vector L with components A, B, and C. R, this says x, these two vectors are equal to one another, so their corresponding components have to be equal. So this says x equals x naught plus AT. Similarly, y equals y naught plus BT. and Z equals Z naught plus CT. So if you can't remember the parametric equations for whatever reason, as long as you know what the vector equation of a line is and you know how to work with adding vectors and multiplying a vector by a scalar, you can come up with those equations on your own every single time if you need to, if you can't remember what the parametric equations are. So throughout the course, I'll use parametric equations, more than I'll use any other equation. So there's the vector equation of a line, and now I'm going to introduce what are called the symmetric equations of a line, and you'll see me use parametric more than anything else, though. I think they're probably the easiest ones to use are parametric equations because it clearly gives you something that we're accustomed to working with: X, Y, and Z. All right, so then solving these for T and equating them, we get the symmetric equations of L. X minus X naught over A equals Y minus Y naught over B equals Z minus Z naught over C. All right, so we'll stop there in this video, and then in the next one I'll do some examples that go over all three of these different types of equations of a line.